The oxygen sensor is an electrochemical sensor, producing an electrical current from a chemical reaction taking place within the cell. The sensor comprises of a plastic housing with a membrane-covered aperture, which serves to restrict the rate of gas entry into the cell. Inside, 2 electrodes are immersed in a liquid electrolyte, a noble metal working electrode positioned across the aperture in close proximity to the membrane, and a much larger lead counter-electrode that sits within the body of the cell. An external low-resistance measuring circuit forms an electrical connection between the 2 electrodes. Oxygen entering the cell is reduced at the working electrode, forming negatively charged hydroxyl ions. The ions migrate through the electrolyte to the counter-electrode and react to oxidize the lead, giving up electrons in the process. These liberated electrons flow through the external measuring circuit to the working electrode, where they're required for the reduction reaction to proceed. The number of electrons flowing through the external measuring circuit is directly proportional to the amount of oxygen entering the cell, as is the rate of consumption of the lead counter-electrode. This consumption of the counter-electrode means that the oxygen cell has a finite life and is a consumable part, requiring periodic replacement. The carbon dioxide sensor is an infrared sensor. Nothing is consumed during the measuring process, which makes it a long-life sensor. The infrared source emits infrared light, which is captured by the infrared detector. Carbon dioxide absorbs infrared light at a specific wavelength. We place a CO2-specific optical filter in front of the infrared detector, which only allows infrared light of the same wavelength as that absorbed by carbon dioxide to reach the detector. As a result, in the presence of no carbon dioxide, 100% of the infrared light reaches the detector. In the presence of carbon dioxide, the gas molecule absorbs the infrared light and thus reduces the amount of infrared light reaching the detector. The reduction in signal from the detector is proportional to the concentration of carbon dioxide present. Each CO2 sensor is individually characterized to ensure we get the best performance from it.